Okay, so today we begin sort of, the first algorithm that you can connect to a practical application directly. I mean, still, I would, refrain from saying that it has direct application to important problems. But, this is an algorithm which has, a direct link with a very important application. Plus, this algorithm can be part of many other algorithms where the similar functionality is required. And the algorithm that we will talk about today is the Grover search algorithm, or it is also known as quantum search algorithm. And initially, the algorithm was presented, and still is mostly described as a way to search through an unstructured database. You have, a collection of certain things, for example, a collection of names, or a collection of items, or a collection of movies, etc. And according to some criteria, you want to find out that which one of the item in the database matches your criteria. For example, if you think about the names, maybe you are trying to find a name that starts with C. If you are looking through, let's say, a database of number, and you want to find a number that is prime, and so on. So, or maybe you are trying to, find a solution to an optimum problem that may have, certain possible routes, for example, from for going from lumps to your home, and there may be, multiple paths, and there could be a database that contains the time that you need to travel through each of those paths, and then your search algorithm should try to find maybe a path that takes the minimum time, and so on. So there are a lot of problems that can be, described as sort of a search problem. Now, if your search space has some structure, for example, you are looking through a space of numbers, and they're all, written like 1, 2, 3, 4, 5, and so on. They're in a certain order. Or if you're looking through a collection of names, and maybe all the names are alphabetically sorted already, then classically speaking, you can speed up the search. You can, there are efficient algorithms available depending on if your data is sorted, but you can do search much faster. But if the database is unstructured, for example, the names are just randomly put in a table, or the numbers in your set, they are just, randomly put there, then to find something, you potentially have to search through, each one of the element in the database, because maybe what you are looking for is, listed at the end of the database. So for unstructured database, the worst case scenario requires searching it the n number of times, if n is the number of elements, in your search space. And even probabilistically speaking, you have to, search through more than half of the database, like n by 2, to get a probability of more than 50%. So this problem was addressed by Grover using his search algorithm that potentially solves it. Instead of in n queries, you can solve it in n square root of queries. So it's a polynomial speed up over the classical algorithm. It's not exponential speed up, but since this can be made part of many other algorithms, this can be used to speed up several other algorithms as well. So today we will discuss this algorithm, and let me share my screen. Okay, and just to let's go to the full screen. Okay, so today we will discuss this Grover search algorithm. This is sometimes also called just quantum search algorithm. And the reason is this, that we will not prove right now, but it can be proved that this is almost as optimal as you can go in searching an unstructured set of elements on a quantum computer. So this is essentially the quantum search algorithm in terms of optimality. Okay, so Let me, first pose the search problem, and then I will describe the algorithm and show how this algorithm works. So the problem is this. Let's suppose you have a set of unstructured database. For example, maybe you have some names, Imran, Irfan, etc. Or maybe you have a collection of some numbers and so on. So what we do for this problem, that we assign an index to each of the object in this database, and let's say the index runs like 00, 001, and like this. You get the idea. So as far as this algorithm is concerned, we are just going to work with the index and not worry how this index is related to a particular database. So this can be names, numbers, or maybe there are some options in an optimization problem that certain things are listed, etc. But the thing is this, that all the answers that you are looking for, they are linked to this index. So now our problem is reduced to searching through this index instead of searching through the database. So we essentially are going to search through this set of solutions like 0, 1, 2, 3, and so on. So this is our index. And this part that relates the index to a particular item that you're looking for, we say that we relegate it to some function f of x, which maps from nth n bit string to a 1-bit string, which can be 0 and 1, such that f of x is 1 if x is your solution, and it is 0 if x is not your solution. So essentially, for the purpose of this problem, we have access to a black box. And the black box implement a function f of x. And if quantum mechanically, speaking in its notation, it maps this n bit input to a 1-bit output, which can be either 0 and 1. And this black box can tell me if this particular index that we are inputting it is a solution to our problem or not. So essentially, we have access to a device that doesn't know the solution, but it can recognize the solution. If we give a particular index to this black box, and for a given problem, this can tell us if this x is the solution that we are looking for or not. And we can represent this f of x by this f of x is 1 if solution is 0 otherwise. And classically, you can see if we have the solution, the set of possible solutions all the way from 0 to, let's say, n minus 1, so that I can represent it on an n-bit register, because 2 power n is equal to capital N. So there are these many number of items in this search set, and we are going to assume that the search set is always equal to 2 power n. And if it is not equal to, you can always add some garbage values to the search space and make it equal to the nearest n, so that we have a total of n entries in the search space. So our classical solution will require us to give each index to this black box as input. So first we will give 0 and check if it gives us 1. Then we will give 1, check if it gives us 1, or then we will put an index 2 here, and so on. So in general, in the worst case, we will have to make n queries of this black box to know that which one of the index is a solution, because it is unstructured. So anyone could be a solution. So in the worst case, we could end up, giving the last index where which is the last index is going to be the solution. So the worst case scenario requires us n queries of this black box to find the solution to this classical problem. Okay, so let me stop here and see if there are any question or confusion about what the problem is. So Manib, you get what the problem, what the search problem is?
Yes, so you have to essentially find the index instead of a, if you have one input, then you have to find its index within that database, give it like.
Good. And this part of recognizing that whether this index is a solution or not, we have relegated to a black box. And this has actually given us the freedom to just concentrate the overall algorithm and forget about, different instances of this such problem, because with this way, we can, formulate algorithm that will work on almost any type of database, because that, difference of database to database, if it is a set of number, set of names, or some movies or something like this has been relegated to this black box function. And now we see that classically, in the worst case, we might need n queries to really see which one of the index is the solution. Even if we have access to probabilistic computer, by the way, which can randomly give each of this index as input, even then, since each one of them have equal probability of being the solution, so each one have 1 over n as its probability of being a solution. So if there are 10 entries, each one is like 10% equally probable of being a solution. So in that case, even then you have to give at least n by 2 queries, that after that you can say, okay, the next entry might be a solution with a probability more than 50% after you have eliminated, n by 2 queries. So even a probabilistic computer is, still giving us, requiring us to have order of, n queries of this black box. You see, when we talk about the number of operations or number of queries required to solve a problem, we don't really, worry about this factor of half or, multiplying by 2, etc. Because if it is, a trillion, half a trillion, and trillion is almost the same. We do worry about, if it is n or n square or n square root, etc. Because if it is a trillion, this is like trillion power, trillion square, which is, trillions of trillions. And this n square root is essentially, just a million if this is a trillion. So we do worry about the powers, but not the multiplying factor or dividing factor or even constant addition when we talk about comparing the, the number of operations required to implement an algorithm. Okay, so let me now go on to describe the quantum mechanical algorithm, and we will see that the quantum mechanical algorithm, quantum search algorithm, can find this answer in n square root operations instead of n. And this actually was shown in 1996, I think early 96, yeah, late 95 by Grover, that this is, a fast search can be performed if a quantum computer can ever be built. And you can see that this is the time that there was no quantum computer really in hardware at that time. But, this algorithm, one of the sort of a stimulant in increasing people's interest in building quantum computers. So this algorithm is important, historically as well, and still is part of many faster optimization algorithms and other algorithms as well. All right, so let's get to this Grover search algorithm. The algorithm is simple, but analysis is a little bit involved. So it will take a little bit of time. So the algorithm is like this. Like most algorithm that we have studied so far, you have, n qubits, and you initialize all of them to state 0. And then you perform Hadamard on each one of them, which is the Hadamard transform. And then you implement the black box function f as part of a phase oracle f, so that it multiplies the input state with -1 raised to power f of x, just like our Dice-Joza and Bernstein-Vazirani algorithm. And it gives the output. And then this algorithm has another Hadamard transform. But now it has a bit more than that, okay? So far, we are used to, seeing algorithms that are only this complicated. It has another function. Some people, would call it another phase oracle, but I wouldn't call it an oracle because it doesn't, access a black box. It does implement a function f naught, but that's a known function. It's not a black box function. So this f of x is a black box function, but this is a known function. But this also is almost like an oracle, and I'll describe it a little bit later. This I'm labeling it with uf naught, and then there is another set of Hadamard. And then in this algorithm, we have to perform, sorry, not this one, but this part. This part has to be repeated. Repeat r times, and we will see how to find this number r. And then after this repetition, we implement this measurement. And we claim that the index that makes this function f of x 1 will appear at this output after measurement once we repeat this process r times. So this is the algorithm and this is the claim. And let's see how we can show that this algorithm works the way that we say it does. So for that, let me start analyzing this algorithm. And suppose this is our input state, and let me call the state that is at this stage some S state, and the state that is at this stage, let's call it some S prime state, and the state that is over here after some, let's call this as psi naught, and the state that is right at the output, let's call it some psi. So I'm going to, analyze the state at each of the states, and we'll see how this algorithm actually works. And the principles that we will learn from this will actually illuminate the way quantum algorithms work in a much better way than the previous two simple algorithms that we have studied. All right, so let's start from the input state. So the input psi naught is nothing but this 0 state, which is 0, 0 on each qubit, and the state right after the first Hadamard transformation is just the state that we have encountered many times before as well, which I can write 1 over n square root sum over x from 0 to n x. Okay, so this is the state S right after passing through Hadamard. And let me now describe the Grover oracle or phase oracle that we have for this algorithm. So the phase oracle that we have this time implements this function f of x. That's 1 if your X is a solution, and it is 0 if X is not a solution, where X, belongs to this set. So X is, either 0 or 1 or 2, all the way to n minus 1. And just remember, the 0 means really 0, 0, 0, 0. This 1 means 0, 0, 0, all the way to 1. 2 means 0, 0, 0, 0, 0, 1, 0, and so on. N minus 1 means 1, 1, 1, 1, like this. So this X is just an index. And suppose for this algorithm that W is the only solution in this set. Like this set contains some element, let me call it W, somewhere, over there, which is a solution. So it means that when X is equal to W, this f of X is 1, and when X is not equal to W, X is 0. So we are now assuming for the algorithm right now, and later on I'll, also address this situation, because sometimes our database can contain multiple solutions. For example, you're looking for a prime number in a given set of numbers. There may be more than one prime number, or you're looking for names that start with letter I. There may be more than one names that start with letter I, and so on. But right now, because it would be a little bit easier to start discussing this algorithm, that we assume that there is only one solution in this search space, and let's call it W. So we need to implement a function, an oracle that implements this function, which means that if you want to compare it with the Dice-Jozsa oracle, that was for the balance function, you have f of x 1 for half of the input, and you had f of x 0 for the other half. But now we have f of x 1 for only one input, and f of x 0 for all other inputs. So if you want to think in terms of phase, so this is an oracle that transform x to -1 power f of x, which actually means that x goes to minus x if x is equal to W, and it remains x if x is not equal to W. And since there is only one solution, it happens only for one value, which means if I prepare the truth table, and suppose this is your x and this is your -1 power f of x, and 1 0 0 1 0 1 1 1 0 1 1 1. So let's say this one is the solution. This is your W, suppose. So then this is 0 0, this is 0 0 1, this is -0 1 0, this is plus 0 1 1, all others are plus. So only one element is getting the phase. So I'll discuss when we do the implementation in Qiskit, that how to implement such an oracle using C0 gates that give a minus sign to only one of the input and none of the other. But right now you can also imagine it like a matrix as well. For example, if you are talking about a matrix, so this is a matrix that is otherwise an identity matrix, except that one diagonal element have a -1, so that when you multiply with that corresponding vector, only that one gets a minus sign, and for all other inputs, if one is here or here, you get the same as output. All right, so okay, so you understand this oracle now, that it gives a phase to only one of the input, and that sorry, not one of the input, but that particular basis state, which is the solution, and it doesn't change the sign of any other state. So I can equivalently write this UF like this as well, that this UF is in operator form, I can write it like this. Let me call it 0, 1, 2, and there is some W state that has this minus sign, then W plus 1, all the way to n minus 1. So which in matrix form is again like this 1, 1, 1. Only one is minus and all other are 0. So this operator, as you can see, will transform any state to itself except the W state, which will be transformed to minus W state. And this, by the way, I can write in several ways. And one of the way of writing this phase oracle is that I can recognize that this is nothing but identity minus twice W, right? Because if I add and subtract a state like this, so if I add a W and then subtract it again, then these two minus WW minus WW becomes minus 2W, and then everything else is just an identity. Okay, so this was plus. So because all other elements are coming with plus, or equivalently, you can think from this matrix. This matrix can be written as 1, 1, 1, 1, 1 minus twice 0, 0, 0, 0, only one here and 0, 0, 0. Because, sorry, let me put plus here. So minus 2 times this, because this minus 2 will be subtracted from the corresponding one and you will get a minus sign over here. So this UF operator describes your Grover phase oracle. Is everybody okay with this?
Yes, sir.
Okay, perfect. So let's now go back to the circuit again and just see. Okay, so I had a state S just after Hadamard, and now I know what UF is, and let me write the state S prime just after the Groover phase oracle. So state S prime is UF operated on S. But before I do this operation, let me rewrite S again as well in a special way. S state is nothing but 1 over n square root sum x from 0 to n minus 1 x, which let me just remind you again, means that it's an equal superposition of all the states, and it includes that your solution state as well with all plus sign. So let me separate it into two terms. One term that contains everything except the solution state W. And let's separate the W state. So first of all, because of orthonormality, you can see that whatever this state is, this is orthogonal to this. Because if you take inner product of W with any one of these, you will get a 0. So this state, which is this minus W, is orthogonal to this. So, but this is not a normalized state, okay? Because now I have n minus 1 entries, and there's 1 over n square root here on the outside. So to normalize it, let me multiply it with n minus 1 square root and divide with n minus 1 square root. And that n minus 1 square root on top, that's right here. So 1 over n minus 1 square root, and this sum, let me write it, x 0 to n minus 1. But now this does not have that, W state in it. So symbolically, I can say x not equal to W, but is sum over everything else. So this is one state plus 1 over n square W. Now this is a normalized state, okay, because this sum has n minus 1 element, and I have 1 over n minus 1 square root here. Let me give it some name. And an appropriate name is W perpendicular, because this state is orthogonal to W. So this is still S state, just right after the header mark, but I have separated it into two states. One is my solution state, and the other is whatever is perpendicular to that. Writing this way, has a nice geometrical interpretation that I can easily see. Because if you look at these state, this square of this and square of this, they add to 1. Okay, so I can call this thing some cosine alpha, suppose, and I can call this something sine alpha. And the reason is this, that if you just see that cosine square alpha, sine square alpha, which is the n minus 1 over n plus 1 over n, they actually add to 1. So I can give it a geometrical interpretation. Remember, I'm done with the state until there. I'm now doing all of this just for the sake of geometrical interpretation. We don't have to write it in terms of angles, but if you do, you sort of get a very nice view, because I can now think of it, this S state, like this. So if I have some sigma plane, which has the W perpendicular on this side and W as this vertical axis, so I can then draw this vector S like this. So my vector S makes an angle alpha with W perpendicular axis, because this is cos alpha and this is equal to sine alpha, and the this vector S has a component, this component along this one. So this is this angle and this much component along this one. So this, if I write it sine alpha, so then now you can see easily that if this S is a vector, its component along omega perpendicular is cosine alpha. And since this S is a normalized state, I don't have to write any a here, because this S is normalized, which means that the magnitude is 1. So cos square sine square should be 1, which is 1. So this component is cos alpha, and the component perpendicular to this along this omega axis is sine alpha. So now I can view this S state as a vector in W perpendicular plane, where this vector is mostly aligned along W perpendicular, but my solution is perpendicular to this, and there's a very small amplitude of this vector along the solution state. And by the way, the goal of the algorithm towards the end would be, if somehow I can rotate my state towards the solution state, what I want to find out at the output. And that's what we will be able to see with this picture. So any question on this visualization thing? And mathematically speaking, you see, it's very straightforward. These two numbers have one parameter n, so I can represent them in terms of two other functions that still have one parameter. So nothing new introduced here. So it's still equivalent. The description is still equivalent. Okay, so now I have written my S state in a certain way. Let me operate this phase oracle UF on my state and get state S prime. So S prime is the state of UF. Okay, so S prime is equal to UF S, and UF is identity minus twice omega ket omega bra into S is cosine alpha omega perpendicular plus sine alpha omega. So this is my UF, and let's operate it. This identity, when it operates on both, I will get them as it is, cosine alpha omega perpendicular plus sine alpha omega. Now when this applies to this, so this omega into omega perpendicular will be 0. So I will get 0. And when this operates on this, omega into omega will be 1 because of their normalized vectors. And I will get -2 sine alpha omega. And now I can combine them. So it becomes cosine alpha omega perpendicular minus. So this is plus sine alpha, this is minus sine alpha. They are both omega states. So I get minus sine alpha omega. So this is my S prime state. And let's see where this S prime state is in this picture. Since this alpha is now coming sine alpha with minus sign, so this component is with minus sign. It means this is equivalent to a vector like this, which now has an angle in on this counterclock side, and this is S prime state. So it means that this UF has essentially played the role of rotator around this omega perpendicular axis, and rotated our S vector from this to this side by an angle 2 alpha. Right? So this is a way of visualizing this thing. By the way, there is another visualization of this thing as well, and let me show that, because that's also, I think, helpful to have in mind. So this input state was 0. All qubits were initialized to 0 state with the same amplitude. And then after Hadamard, we got S state, where each of the the 0, 1, 2, 3 all the way to n-1 states, they had equal amplitude. Even our W state had this amplitude, W plus 1, W minus 1, and so on. And the amplitude was 1 over n square root. But now after we have performed UF and gone to this S prime state, this still the amplitude are exactly the same as they were in the S state, because you see this is the S state. So S state and S prime state, they have the same magnitude of amplitude. The only difference is that the amplitude of W has gone from plus to minus. So S prime can be pictured like this: plus, plus, plus. But W is now with negative amplitude, and all other states have positive amplitude. So this is what the Grover phase oracle did, that it marked this solution of this search space, marked by inverting its amplitude. Okay, any question on this visualization? If not, let me go back to the algorithm again here. So this is the algorithm, and now I'm left with this part, that I have to perform Hadamard again, a UF naught, and I still have to define what UF naught is, and then Hadamard again. So now instead of passing this state S prime through each of the stage individually, let me prepare an equivalent operator for these 3 layers. This operator is called V. You can call it by any name, but this is called diffuser. Actually, this was called diffuser by Grover himself, and I'll talk a little bit about why. But this combination of these 3 layers is this diffuser operator. And let's first build this operator, and then we will apply this operator right on this state as prime to find state at the end of this diffuser. And for that, let's start discussion from UF naught. So this UF naught is just like the Groover oracle, but it works like this. So this is a fixed one. It doesn't depend on the solution. Remember, it doesn't depend on solution. It has this fixed answer that it gives 1 when x is equal to 0, and it gives 0 when x is not equal to 0. So basically, if you have any state other than 0, it lets it through as it is. But if you input it 0 state, it will give it a phase flip and put a minus sign, because this f of x is 1 only when x is equal to 0. So this is a fixed function. This is not a solution dependent function. This is not accessing any black box. Okay, so this means, by the way, as you know, that this is equivalent to saying this, equivalent to this thing, that this f of x is equal to 0 when x is equal to 0, and it is 1 when x is not equal to 0. Okay, and the reason is this, this and this only have a global phase difference of because this means that you give a negative sign to every state that is not 0, and 0 to the state that is 0, and this is the opposite. So the overall difference is that this is f of x, and this is essentially minus f of x. So it doesn't matter. You can, when you are implementing it, you can implement it any way you like. Okay, so let me write it. Its function operator form UF naught, and if we choose this form, we can get the final state as W instead of minus W. So when we are going to work out the analytical part, we will choose the function form like this, that it gives a 0 phase for 0 input, but it gives a negative phase for all other inputs. But when we are implementing, we will actually implement it like this, because that's a bit easier. I will have to give a minus sign to only one input and not everything else. But when we define it like this, I will have to build an oracle to give a minus sign to every output except for 0 input. So implementation wise, this is better, but for analysis purpose, this is better, because I will not have to worry with the overall negative sign with the state. So I'm going to define this UF naught for a function f naught of x like this, that this is 0 when x is 0, and this is 1 when x is equal to not equal to 0. So in this case, I can define this UF naught like 2, 0, 0 minus identity. Okay, and you can see this essentially is like this, that my 0, 0 minus 1, 1 minus 2, 2 minus 3, 3, and so on. Because this UF naught will give a minus sign to each of the input except 0. And if I subtract and add this term, so let me add this term here and then subtract this term again. So that this part is essentially no identity. And these two terms can add up to make 0. So this is minus 2 identity. And if you think, in terms of matrices, you can write this UF naught like this, that it gives +1 phase to the 0, 0 state and -1 to all other. And since I can write it like this, that this is 2 times 1, 0, 0, 0, 0 minus this identity, because 2 into 2, 2 minus 1 is plus 1, and then this is 0, 0 minus 1 minus 1, 0 minus 1 minus 1, all the way. So this is a form that I can again write 2, 0, 0 minus identity. Okay, so everybody understands this fixed phase function UF naught, which is part of the algorithm. All right. So let me check the chat. That is there, if there's any question. No, okay. All right, so let's now, build this diffuser. Diffuser is nothing but a Hadamard transform followed by the UF naught and then another Hadamard transform. So let's work it out. Let's put this UF naught here. So Hadamard 200 minus identity Hadamard. So this Hadamard will operate from this side, this Hadamard from this side, and I will get 2. By the way, these are also the n-bit states, just to be more precise. 0 Hadamard and minus Hadamard into Hadamard. But this is nothing but Hadamard square, and Hadamard square is identity. So this is identity. And this thing, if you recall, is nothing but S state. Similarly, this is S cat and this is S bra. So this V is just 2SS1. And just to show you that this S is, let me go back to the definition of S, that where the S state came from. Yes, so this S was a state that we got from 0 after operating Hadamard. So this Hadamard into 0 is nothing but the S state, which, by the way, we have written in terms of cos alpha and sin alpha like this. So this is again S state. All right, so now we have been able to express our 3 layers of the algorithms, H, V, H, UF naught, H, as this operator V. So now I'm ready to write the output after passing through the Hadamard, and that is, let's call it something V S prime, and my V is 2 SS minus identity, and S prime is, sorry, I have to operate this V and S prime, yes, and S prime is cos alpha W minus sin alpha W, and which one is the perpendicular? So the cos alpha is W perpendicular, minus sin alpha is with W. Okay, so this is perpendicular. Now I have to also substitute for S. So 2, and this S is cos alpha W perpendicular plus sin alpha W, and this S bra is cos alpha W perpendicular bra minus plus sin alpha W as it is, and then minus identity into cos alpha W perpendicular minus sine alpha W. Okay, so I will have to work out term by term now. So for that, let's see what this term is. So 2 into cos alpha W perpendicular plus sine alpha W. Now this W perpendicular, when this multiplies with W perpendicular, I get 1 because of orthonormality and cos square alpha. When this W multiplies with W perpendicular, I will get a 0. And similarly, when this W perpendicular multiplies with this, I will get a 0. And when this W multiplies with W, I will get 1. So minus sine square alpha, like this. And then I have to multiply this minus identity with all of this, and I get minus cos alpha W perpendicular plus sine alpha W. And now let me collect all the term with W perpendicular sign, and they are 2 cos alpha. Actually, I can, yes, so W perpendicular is here 2 cos alpha into cos square alpha minus sine square alpha. So 2 cos alpha cube minus 2 cos alpha sine square alpha minus cos alpha into W perpendicular. And then similarly, the terms for W would be 2 sine alpha cos square alpha minus 2 sine cube alpha plus sine alpha into W. And I leave it to you to show that this is nothing but cos 3 alpha. You can expand cos 3 alpha and check, and this is nothing but sine 3 alpha. So this is the state after applying the diffuser V. And if you want to plot it on the same graph that we plotted this S and S prime, let me do that. And the last state that we got is, let's call it some Vs prime. So it has cos 3 alpha and sine 3 alpha. So it means it has this total angle 3 alpha. So if you just talk about the angle with this axis, this is just 2 alpha. So basically what the diffuser did, it rotated this state S prime to this state by a total angle 4 alpha. And overall, this initial state S, which was making angle alpha with W perpendicular axis, has gone on to making angle 3 alpha with W perpendicular axis. Let me actually show it in a figure again, because this is really important to see. So this is W perpendicular axis, this is W axis. Initial state S was this. After the first Hadamard, it was making angle alpha with the axis that is not our solution, and it was making a large angle with the axis that was our solution. So small component along solution axis. We passed it through Grover oracle. It came back here, and then when we passed it through the diffuser, it went from here and to this state and became Vs prime. And total angle with this axis is 3 alpha. So this additional angle is 2 alpha. Now you can see it has larger angle towards the solution, larger component towards the solution, and smaller component than before towards the axis that is not our solution. So essentially, if you think about this WW perpendicular plane, Grover developed an algorithm that rotates the state vector from the axis that is not the solution axis towards the axis that is the solution axis. And if only we are somehow able to rotate it all the way towards this W axis so that it has its major component along W and smaller than W perpendicular, and then we measure it, we will most likely get this W as solution and not W perpendicular as solution. And this is actually how this algorithm works. And the idea is this, that in one step, you are able to rotate by 2 alpha. So this was your starting state. So you went from here to here, 2 alpha angle in one iteration of UF naught and diffuser. So let me draw the circuit here again. So we started in the 0 state. We applied the Hadamard. We applied UF. We applied the Hadamard again. We applied UF naught. We applied the Hadamard again. Now this part we call diffuser, and the reason actually is this. If I make this plot, the other visual representation in terms of basis, state. So this shows me that the states W's that are other states that are our solution state, their component has increased to sine 3 alpha. And the state W perpendicular that are not our solution, their component has decreased to cos 3 alpha. Remember, when you increase angle, the value of cos decreases. So cos 0 is 1, but when you increase angle from 0 degree to higher angle, the value of cos decreases. So this angle has increased, this amplitude has decreased. On the other hand, this angle has increased, so this amplitude has increased. So what has happened, that let's say this is the amplitude of states other than W. And this is now the amplitude of the state that is W. So this is W. So it's called a diffuser because this amplitude, the amplitude of this, W state is it's sort of being diffused to other states. So it was on the other side over here, and then some property diffused to other things, and then this grow in size. Even though perhaps a better name, could actually be a reflector, because there's another way to visualize this thing, and it is like this. If you look at this UF, just flip the state so that the average amplitude of all of these states is something like this. So this is the average amplitude of all of these states, because this has become negative. Over here, the average was here, okay? And the UF actually decreased the average. But then when it went through the V, this was reflected around this axis, and this went from here to here. And these were also reflected around this average, and this came to this value, this came to this value. So this is the new value. So they are essentially being reflected around average by this diffuser V. So perhaps a better name is this reflector. It's reflecting around the average value of this function. But the name depends on the way you visualize these things. I would actually like to call it a rotator, because this is what it's doing in the state space geometrical view. And that, to me, is one way of visualizing what quantum algorithms do. Quantum algorithms essentially start with a state vector and try to rotate it towards the state that you want at the output, so that the probability of your desired output increases and the probability of your undesired output decreases. And this essentially is the same view. And this actually has a particular name as well. This is called amplitude amplification, where we increase the amplitude of the desired state and decrease the amplitude of the other states. All right, any question? If not, I would like to actually take a small break, and then we will resume this next part, that how we can make sure that instead of this vector being rotated to only this part, how can we bring it all the way closer to this axis? And then also we will discuss the situation when we have multiple solutions instead of only one. Okay, so let's start again. And before I, continue, let me know if you have any questions. All right, if not, let's, resume, and let me summarize again that we applied this UF that took this S state on the other side. Then we applied this diffuser V. It took the state right from here to here. So the total impact of UF and V is rotating the state by 2 alpha from here to here. So if I describe the total impact of UF and V combined on state S, it went from S to S prime and then to S, another state, which we are calling VS, that was like this. So let me write S again. So S was cos alpha omega perpendicular plus sine alpha omega. And once we apply this VUF, it went to cos 3 alpha plus sine 3 alpha omega, which is essentially cos 2 alpha plus alpha, because alpha was initial angle of this state S, plus sine 2 alpha plus alpha omega. Now, if I apply this VUF R times, then this state would becomes cos 2R alpha plus alpha, because each time we apply this, it will rotate by 2 alpha. So 2 alpha will be multiplied by R omega perpendicular plus sine 2 alpha plus alpha omega. So 2 R alpha. So it means that after R application, our state S went from making angle alpha to a state that makes an angle 2R alpha plus alpha with the omega axis from omega perpendicular. And we can now work out what R should be. If we are lucky, what we can do is make this angle 2R alpha plus alpha equal to pi by 2, so that this state exactly aligns with W axis, so that the probability of getting W perpendicular, if we just measure this state, let's call it some state psi at the end, then if it is completely aligned with this, the probability of error would be 0. But in general, it cannot be completely aligned, right? Because when we start S, this alpha may not be such that 2R alpha plus alpha becomes exactly pi by 2. So this alpha, could be a number such that if we add 2R alpha, we might end up here or here on this side. So let's compute R. If in this, lucky case, that would become 2R plus 1 into alpha pi by 2. Let's take this alpha to the other side. So we get 2R plus 1 equal pi over 2 alpha, and then 2R equal pi over 2 alpha minus 1. This gives R is equal to pi over 4 alpha minus half, where alpha, if you recall, was sine inverse 1 over n square root. And if n is large, this sine inverse 1 over n square root is nothing but 1 over n square root. And if I put this expression over here, this r becomes pi over 4, and this 1 over n square root goes up minus half. And you can see if we just talk of the order of n, then this r is proportional to n square root. And if we want to find exact value of r, you will see that it would be somewhere less than that, because this number in general is not going to be an integer. This, if it is like say 3.5, then your r is 3. If it is 4.1, your r is 4, and so on. And there's one trouble with this algorithm, and that is if we keep applying r, if we keep applying this VUF, it doesn't matter. It doesn't mean the solution will get better and better, because it will keep rotating along this side. And once you get past this axis, you will go here, you will go here, and you will start going away from the axis again. So therefore, it is important to compute R before you start applying this algorithm, because if you apply too few of these VUF operations, you will be far away from W. And if you apply too many of these, you will get past this axis towards the other axis. And in general, you will not end up with this state exactly aligned with W axis, but in general, there could be this, angular gap, which is as large as alpha. Okay, because if we, let's say this alpha is 20 degrees, so then when you apply R once, you make a rotation by 40 degrees, so you reach at the angle of 60. If you apply R again, you will go to on the other side, because the total angle would be 100 degrees, because 20 plus 40 plus 40 would be 100 degrees, and we will be here. So actually, we will be anywhere close to alpha by 2. So let's compute the error. So if you are not perfectly aligned, so let's see what is the error proportionality. So if you start from alpha, in general, you could be, closer to this axis of the order of alpha. And in that case, the probability of measuring this state would be, probability of measuring W perpendicular would be sine square alpha, right? Because if this is angle alpha, this vector still has a projection which is equal to sine alpha, and the probability is the square of this component along this W perpendicular axis. So which is nothing but sine alpha square, and sine alpha was nothing but 1 over n square root. So your order in the final answer is proportional to 1 over n, which means that if n is million, your probability of error is extremely small. It's 1 over million, and this error probability becomes smaller and smaller when this n becomes larger and larger. All right, so any question? And you can also see that after R operation, our state psi is given by this, which means that we have a large probability when we measure of getting this W state at the output than this W prime, because W prime has a coefficient which is cosine of this angle, and we are trying to take this angle close to pi by 2, so that this cosine pi by 2 is 0 or close to 0, and this sine pi by 2 is 1, or this sine of this angle is close to 1, so that our final state psi is almost equal to W. Okay, so before we begin its implementation, let me discuss its case when we have more than one solution. And suppose there are mu number of solutions. Which means if we have this search space, there may be W1, W2, all the way to W mu solutions in this space that satisfy this criteria that f of x is equal to 1 when x is equal to wi, where I goes from 1 to mu, and it is 0 when x is not equal to any of these wi. So suppose there are multiple solutions, and more precisely, there are mu number of solutions. In that case, I can write the superposition state S right after applying Hadamard state like this. So just to recall, this state was this 0, 1, 2, W1, W2, all the way to W mu, and all the rest of the state. So this is an equal superposition of these states. So in the same fashion, I can separate the states that are not solution up to W1 minus 1 plus and W mu plus 1 all the way to n minus 1 separate, and the rest of the state that are solution into a separate vector. And now you see, these are n minus mu entries because mu of them has been grouped into this thing. And to make this normalized state, I will have to divide it with n minus mu. So I multiplied with n minus mu here as well. And this is now a sum when x is not equal to wi. And similarly, these are mu states. So to normalize them, I multiplied with mu here. And this n is already here. So 1 over mu. And this is now a sum over w from 1 to mu wi. And now let me call this my w perpendicular, n minus mu over n. And let me call this my w state. Or this time, this w is a superposition state of all the solution states. And after this, it's straightforward. I can define this as cosine alpha and this as sine alpha. Now sine alpha is mu over n. And again, you do this processing in the same way. You can rotate by 2 alpha when you apply the UF and the diffuser. So ultimately, we end up with the same analysis, except now that when we compute R will be pi over 4 alpha minus half, where alpha is now sine inverse of this. And if n is large, this is 4 mu over n square root minus half. And this is equal to pi over 4 n over mu square root minus half. So R is then of the order of n over mu, which makes sense. If there are more solutions, we should be able to convert faster to the solution space. If there are, like, let's say 100 atoms and 10 of them are already a solution, which means that we will reach that stage in 100 by 10 square root, like in just 2 or 3 application of the UF and diffuser. Okay, so any question regarding Grover's algorithm?
Sir, if we do not know the number of solutions in the data set, can we
Excellent
not
question.
use?
So your actually question is extremely excellent. The reason is this: see that R very strongly depends on the number of solution mu, because it depends on alpha. So alpha is mu and independent, and if you don't know how many solutions are there, you essentially don't know how many times rotate, and your algorithm is not applicable. You won't be able to apply the algorithm because it would be unknown to you where you have to go, and you might end up even rotating much more or much less than you're supposed to. So for the Grover algorithm to apply, actually you have to know the number of solutions to apply. Now the resolution of this problem will come when we, in the next week or the following week, we study an algorithm known by quantum counting algorithm. So that algorithm can count the number of solution in a search space without finding the solution. And then we will have to run the algorithm in two successions. So in general, the quantum computing algorithm, quantum Grover algorithm will always be superseded by quantum counting algorithm. And this algorithm will give us R. And then we will use it to, run the Grover search algorithm. And then we will able to find W. So there are going to be two applications, successive applications of this algorithm. And this quantum counting algorithm we will study after studying the quantum Fourier transform and quantum phase estimation algorithm, because it's based on these two. Okay.
Okay, sir. Thank you.
Perfect. So the good thing is that we have been introduced now to a very practical algorithm that have some flaws that you first need to find R, and we still have to learn how to implement the oracle for this, which we will do in the next stage. Is there any other question on this algorithm? If not, let's do the activities for today, and I will discuss its implementation in Qiskit tomorrow, where I will first talk about the design of a general oracle that you can use to mark desired number of solutions. So far, we had worked in designing oracles that mark half of the inputs, that they give -1 f of x is equal to 1 for one half of the input, and for the it's 0 for the other half. That you get a minus sign with half of the input basis state. But tomorrow we will first learn how to design an algorithm that you can use to give a negative sign to either 1 or 2 or 3 or any desired number of input basis state as you want. And we will have a systematic way of designing it, and then we will use that systematic design to implement the Grover algorithm in Qiskit. Okay, thank you. Let me stop this recording, and then we will